great pleasure to introduce the second speaker of the morning. It is François Ledrappier, who will start his shared mini course on the dimension of stationary measures.
Thank you. And yeah, I understand what Daniela said. You feel like you are on a stage. Okay, so what we want to talk about dimension of stationary measure. So it's a joint term, and mostly what we'll explain it's around and some about and a little beyond and a little before a paper, a joint paper with Pablo Lessa. Which is an archive, so if you don't want to come, you are welcome. Okay, and so we gave more or less the plan, and we will follow the plan that is in the program. And in particular, today I will say generalities about the dimension and statement of it. In this first lecture, so generality about dimension and statement of result. The result is about the title is the paper is exact dimensional measure, exact dimension of stationary measure. So two things to introduce. What does that mean, exact dimension? And in which setting are we talking about stationary measure? So the setting will be random walk. That's for the end of today's lecture. But I want to start by talking a little about exact dimension, because it's a notion which I like very much, and which is I like it. So I have a metric space. And mu about measure. And you want to say that attach a notion of dimension, but on that object, not really on the space, but on the measure. So you want to understand what kind of set the measure is carrying. And a good way of doing that is to look at what's called the local dimension. So dimension at the point x, I take x in the space. And I look at the local dimension, which is the limit of r goes to 0 of log of the measure of the ball divided by log r. And of course, you don't know whether the limit exists. So you have two notions, the lim sup and int, and you have a dim sup and dim int. So that's something which exists. And it's a number which depends on x. And it's what it is. If you have a surface in R3, if you take the area of the surface, this limit exists, and it's 2 on the surface, it's minus infinity outside. So it tells you something about the math. And it's 2 if you have an area. So it's a dimension. And the definition. So we say that mu is exact dimensional. We decide whether we put an hyphen or not. I don't know. So, exact dimensional if for mu almost everywhere. This limit exists. We'll see. Mu, and then we call it mu. No, that's not what I want to say. Is there is not only the limit exists almost everywhere, but there is a constant. Delta, such that for mu almost every, what I was writing, the limit exists, and it does it is at the same value that, like it was 2 for the area. So there are two things which in some sense it's rather weak, because here the limit is only you have a limit, that's something to be happy with, but the limit in the weak sense is just a log. It tells you that the measure of a ball is epsilon to the delta, but okay, up to some error. Okay, that's something. And the other point, which is important, but a priori it's also a weakness, it's only for almost everything. So all the theorems about the exact dimension are ergodic theorems. The same flavor as ergodic theorems are convergent almost everywhere, and you have many points for which the value is different. And you have all, we won't talk about that, but all the multifactorial analysis, we say understanding the points where the limit is different. Okay, and it's related to the Hausdorff dimension. Well, maybe I recall what is the Hausdorff dimension, but if I was set in X, I look at the cover of A by a ball the inside epsilon I is epsilon I lower than R. So R cover of A would be a cover of A by ball radius. And now I take the best. And now for a fixed. Yeah, R and epsilon. Okay. I think the best cover, the infimum over all epsilon cover of the sum something new. I said after the big R, and let me finish the and then I look for the sum of epsilon I to the R. So you see, you have some way of measuring, and this is an exterior measure. Right? You take an infimum of some quantity that you associate to all cover. So that's the entire measure, and then you take what you call the HR of A with the limit of the two and If you don't go to 0, it's bigger and bigger, and yeah, if you have a cover with small epsilon, it was already counted, so it's bigger and bigger. And then if you don't go to 0, you have a limit. And the Hausdorff dimension of A, so you have epsilon which occurs by the power. So if you take two different values of R1 and R2, I mean, if one of them is finite, the other one would be 0, and if one of them is finite, the smaller one would be infinite. Because you always multiply by epsilon to the R1 minus R2 for each cover. So it's easy to see that there is what you call the Hausdorff dimension. So A is the increment of R, so that each R. No, not the right. Just have to be careful in order to have the same definition in the dimension is given. Yeah. It was, I changed the thing 70 times, but thank you. Yeah, I changed to R in my notes afterwards. Okay, so Hausdorff dimension is the quantity which is well known and well studied, which measure how complicated it's not manifold or it's not very smooth. And it's related to, there is a fact. There is a relation between those two notions. So assume mu is exact dimension with dimension. So, then delta is the instrument of the Hausdorff dimension of set of positive dimension. And also the instrument of Hausdorff dimension of set of full measure. So if you have a set of positive measure, it has to be at least mentioned. And cool. The instrument. If you have a set which has full measure, it has to have at least the dimension delta. Or even a set of positive measure, they have to have at least the dimension delta. Why you have to two? Because I mean here I have a constant. If you don't have a constant, if this is a function, then the two are different. This is essentially interesting. No, yeah, that's why E minus A. Boyle measure, it's local. It's a local property. You don't care about the local property. Measure of both. It might be infinite. Yeah, you're right. Right. Okay, finite. Finite, but it makes sense also for radon. For radon, it makes locally compact. Yeah. And the hint for the exercise is the Vitali lemma, which is very yeah. No. You can have you can have even significant measure and the back the complementary dimensional. So the hint, which is very, very important anyway, the Vitali lemma. On trouve en général séparable matrix space. Did I say separable? I didn't say separable. And so A and B covering of A by both epsilon. Then there is a family of disjoint balls from the covering such that the union over I of B psi 5 epsilon I cover. So you can find a subfamily with of disjoint ball, and then by enlarging a little the ball, by enlarging a little by 5, then you cover it. So no, I mean, I prefer the lemma, but it's true only for it's true only on the Riemann, I mean, Lipschitz equivalent spaces, but this one is completely different. Yeah. Okay, so what's good about it? What's good about this statement? That often for many, many examples, it's the only way of getting an estimate on the estimate from below on the observed image. There are many sets which look a little complicated. You try to work out the dimension. You find an upper bound quite easily just by the geometry. And then you want to show that the lower bound is exactly that way. And I know most of example is by choosing a good measure, the good measure for which will be exact dimensional, and we'll have a dimension will be the upper bound that you already find. So you have the upper bound, you try to construct a measure which is not. And an example of which I like very much. Felix also likes it. So yeah, that's the opportunity of thanking the organizer for inviting me. The example I like is the Weierstrass function. The graph of the Weierstrass function. It is not the Weierstrass function of the usual one, but it is the one which is famous in the harmonic analysis, which is here from n to infinity of lambda to the f. So be integer and lambda. If lambda is smaller than 1 over b, its function is T1. It's legit, at least. When it's smaller than T1, so the derivative is double. But if lambda is smaller than 1, the continuous function. But in between, you have a graph, which is nice and something like that. And it was shown by Admissible. So in 37, that the Hausdorff dimension is smaller than of the graph. It's smaller than 2 plus the lambda of b. The lambda is negative. But, and it was popularized under the inequality. The inequality was asked, but it was really popularized by Mandelbrot. He wanted to call it Weierstrass-Mandelbrot function because he asked the question. And it was shown recently by Ratio Shen. We know. Someone who we know, and it works with dynamics. And it's a paper in 80. And in between, there were many tentatives. It was really a very popular problem. And the way we should prove it is by taking the natural measure, the one which projects on the bag on the static. You lift it in and you work with that measure and use the fact that there is some dynamic hidden. It's a result of the dynamic computing. And there are many partial results. The best one are by physics of the part. What? And so you have to prove some ergodic property on that measure, some almost everywhere limit. So you prove that this measure is a black dimension. With dimension. That much. Okay, if you want to know, I mean, there is a yeah. What is he asked the question. He asked exactly the question, and he claimed that he was the first one to really understand what was an important question. So it's just 40 years to win, to go from fringe mathematics to general audience. Still 40 years to come. There is a nice clipping about all this and much more. By Matthew Elfner. It's called scale. And archive. He has a general, he replaces the log by another function. He has a general theory of scale, and we have different scales. And so if we have similar theorem for with a very good notion of Hausdorff dimension, and also packing dimension. I don't talk about packing dimension, but it's also enter the shift instead of there is a whole zoo of things to do, and in the paper of Mathieu, it's very good perspective. What are the properties? There are properties which are elementary. If I take two objects like that and I make a product, that is the product, that is the on the product, and I take the product with them. If mu1 and mu2 are exact dimensional, then mu1 plus mu2 is exact dimensional with dimension delta 1 plus delta 2. Completely trivial from the definition. Another fact which is easy Pablo, have you explained that question? Sorry. Oh, okay. And I think they're not. Another fact which is also easy, if I have some object like that, and I have a mapping phi into another one, y. And let's assume that phi is Lipschitz. Then it's true for both dimension is independent of phi of the image measure, phi star of u, is smaller in dimension 6. And that's clear because the pre-image of a ball contains the ball. And you divide by log r, which is negative. So I just wanted to underline that your good intuition is that the perimeter of the ball is contained in the ball. So you write something to and you divide by a negative number. So the result is in the other direction. So you might want to be a little more precise if you know something about the fiber. So as I'm in the same situation, but now I've
Are you assuming that the magnitude is the correct dimension?
No. Yeah,
The map by is protected.
no, but you don't use that because it's only on the image that you say something. So you have fiber, and when you have measure on the projection, you have disintegration. So there is this. It's only this. Y, so maybe I assume you is finite. But I mean, it doesn't depend if I replace by if I anything measure I replace by finite measure with the same but anyway, as you find you finite the family of the integration. So what are those? So these are measured. So for each one. Yeah. Yeah. Both everything is defined. So it's a family of measure, mu y. So that mu y is supported by the fiber and mu. If I take any function f, integral of f of can be decomposed as an integral over the image measure of partial sum over final sum of the you assume separable, yeah, separable. Yeah, you need separable. Yeah. Separable. Yeah, I knew, but but mostly I'm opinion basis on but okay. Okay, so you have this family, which in fact we give you some details about this project. And if I assume that for almost every y, Mu y is a measure on the fiber, so it's a measure on X. So it makes sense to is exact dimensional with dimension delta. Yeah. Then okay, so if D is Lipschitz equivalent to an equivalent space, and I'll say a word about that. So if you have some regularity on the space, you can compare to the with the same delta is the same for almost every y. So almost every y, comma. Mu y is exact dimensional with dimension then. Yeah. Is that I upper sign? No, no. Then what? The dimension X, the dimension of mu is at least the dimension by mu. That's what the same as this one. Plus, but there's a gap between the two. If I know that the condition, yeah.
Yeah, sorry, after the death, but
If it is put together. Why do I put that? I wanted, but I was sick last week. So I wanted to prepare it with using only Vitalis Demat, but I was sick last week. I couldn't. So, so I have this statement, which is cool. If you assume it's equal, because it uses the Lebesgue density theorem. But it should be doable. Exercise. And pi is Lipschitz theorem is still pi is the continuation of it. Okay, so that's an exercise, but you're using Lebesgue density theorem on X. And I suppose it's also doable using a different but I didn't do it. Yeah, since I just erased the graph of the layer class function, it's a good example to show that in general you have inequality here. Because I mean the measure I was talking about, the one which projects on the bed. So it's a graph. The conditional measures are just Dirac. The conditional measures are exact dimensional with dimension 0, for example. But we know Chen told us, and that was known way before, That's the dimension of the graph. Two plus b, which is bigger than 1. Lambda is bigger than 1. So we have this, but typically, if we are in the fractal world, that's one of the things. Right? Yeah. Maybe. Maybe. A priori, yes, but no, I haven't written it, so that kind of thing. Any any common sense answer is wrong. So okay, so I wanted to make a few examples very quickly. A few examples, a very classical example to see what it is about.
I'm sorry, it's my voice. In that example, the higher stress function is not really.
No.
So if I put the that's it.
Yeah, but it's not I'm trying to get our government nothing. That's why. Yeah, that's the point. Okay, so a few examples, very, very classical examples. You all did that in the not that presentation. So you have once the classical counter, I cut in third, in 3/3, and I keep the result, and I keep the instead, and I put the measure on CN, which each atom is 1/2 CN. I have two to CN pieces at stage n, and I put the measure 1/2 CN for all of them. And so if I try to compute the ball, if I take any point in the counter set, the ball of radius 3 to the n contains one of the ball of radius 2 to the minus n contains one or contains at least one interval, and contains the measure is between factors n. So if I take the log and I divide by log of 3 to minus n, I get log 2 log. Again, even in that case, it is it's a clear estimate from above of the order dimension of the Cantor set. And the simplest way of saying that it is indeed of dimension log 2 over log 3 is to exhibit this measure and to use the result. Even in that case, it is very convenient. So you might make things a little more complicated. So instead of taking that measure, I take the Bernoulli measure with the probability P and 1 minus P to the right and 1 minus P to the left. And so what is now the measure of an interval of stage n? It depends. P the number of times I went to the right, 1 minus P the number of times I went to the left. So if you look at what it means and you use a low large number, you get that P is exactly equal. With dimension. What do I get? I get you have to use you get the integral of log so it's minus 2 of P. P some quantity numerical one divided by. And now I still do things a little more complicated. Instead of setting by 1/3 and 1/3, I take lambda here and the rho to the right, and I continue the same. Here I take lambda and rho. Here I take lambda and rho, and I go on. But now, so the typical measure, and I take the measure. The typical measure of an atom at stage n will be the typical length will be lambda to the power of the number of times I went to the left multiplied by rho to the power of the number of times I went to the right. So into we get and down there you get the exponent. And that's the general fact that at least in dimension 1, that's the case where the computation is easy. There are cases where it's a little more complicated, and there is a fancy preprint by people in the audience. The most general. Oh yeah. There's another example which I like. So you can, of course, you can have an expanding map. For instance, in a Gaussian. And if you get, there is a famous result of Jarnik in number theory. It tells you that the Hausdorff dimension of constant type numbers. One. So now you can consider the Gauss map and look at the set the attractor by forgetting all the coefficients which are bigger than capital N. So, so you get AN, which is the set of constant type numbers with expansion always smaller than n. And you can try to apply the corresponding formula, entropy divided by each set which is invariant by the Gauss map. You can try to to compute, to estimate the other dimension by taking the entropy divided by the exponent, and it's about. But you can make estimate, not find the best measure, but you can find a good measure which is Markov for a finite number of steps, and which will give you some estimate, and the estimate goes to 1 and n goes to 2. So I think it's but the real, I mean, the good measure is the Gibbs measure, but you cannot really compute, estimate estimate the exponent and the entropy with enough precision. And yeah. In the right. So I'm saying that for an expanding map, it's still the entropy divided by the exponent, the same formula. The product each time you if the measure on the stage n, it would p to the power of the number of times. Yeah, and then you have the same measure. You have the same term on the top, but the down is the width, and the width will be given by the exponent. This is given by Cohen's formula, which is that you try to you try to find the so you have log x prime, the derivative of the slope, and you you try to find the s, so the pressure of minus s log x prime is 0. And that s and the corresponding equilibrium measure will give you with the exact dimension again by the other square, and the dimension will be exactly that s. Yeah. So AN of Pablo by N. But oh, okay, great. So you can go much further. You can do something which I like, which is random walk. Not only iterate the same differential, but you can do a random walk on the differential. And then you will have something analogous, but I won't stay here because there are people in the audience. With Weicho A, Yushan Yao, and Dinshan Chu. We have also a preprint on archive. And it's even more recent than on April 3, 23. For the same kind of it, and if you have questions, ask them. Again, I was sick last week and didn't have time to prepare. Okay, so the remaining 5 minutes, I wanted to state the result, but I will not state the result. Yeah, I can say. What are we talking about? So that was what I wanted to say about exact dimension, just to make some advertisement for that notion, which I like very much, and which is somehow useful. So what we are applying to is applying to random walk. So the first course about the A part and the B part of 3 minutes. If we have so given by we have some measure mu on a priori GLDR, but the determinant is very easy to understand. So I go directly to Oseledets. And what a random walk is you form the product, you form the independent product of this method, of equation chosen with you. So the mathematical formalism, if you want, is omega n. And then I form Dn the coordinate. The coordinate mapping, and I form Hitchin omega. So I found this product. Why the definition? I want to give the cycle. Omega. I hope it's the right one. So if I take this definition, I get the cocycle of it. And same as the derivative. Okay, so I have this object. And I make some hypothesis on mu. I will assume that the log of the norm of D is finite. And then I have Oseledets one, which I have 30 seconds to read. And okay, which I do tomorrow, but well, I'll give the precise definition tomorrow. But for people in the know, what Oseledets gives you, it gives you a family of bases. You want to remember the random decomposition of RD. I will explain what it is tomorrow. So that's for people who know already what it is. so that I can take our result. So it's a random decomposition, so it's an object. This decomposition is an object for in that space. Some space, another space, of dimension V1, another space of dimension V2, another space of dimension V3. So I have a random object in that space. It has a distribution. And the result is that with the hypothesis. I just look at this object as a sequence of spaces. After my hypothesis, I'll come back tomorrow again. Then what we want to understand is where distribution of is exactly. So that's our result, and I will explain. And Pablo is, the ingredient of the proof, and there are, I think the ingredients are it's the result, but understanding where it comes from and how it works. The gist of the lecture.
Are there any questions or comments? Maybe not. Okay, so the next lecture will be in 5 minutes.